Last time we saw how we can obtain the impulse response of the ideal low-pass filter, the sinc function. The problem of this impulse response is that it's non-causal, and we also cannot make it causal because it starts at minus infinity. We cannot add infinite delay. So here is our sinc function going from minus infinity to plus infinity. Assume we would like to have a causal finite impulse response, FIR low-pass filter, meaning the impulse response starts at time 0 and extends over only a finite amount of samples and goes from 0 to L minus 1 for a length L. So observe that FIR filters have no correspondence in the analog domain. Analog filters always have an infinite impulse response, IIR. How do we design this filter such that it becomes similar in some sense to the ideal, since we cannot get the ideal filter? So let's take a look at this example. We will design an anti-aliasing filter for sampling rate conversion. The original signal is from a CD with 44.1 kilohertz sampling rate, hence an audio bandwidth of about up to 20 kilohertz. And we would like to downsample it to 22 kilohertz sampling rate, for example, for a Mac computer. In order to be able to downsample it, we first have to low pass it. For instance, the pass band should be from 0 to 9 kilohertz, and the stop band, to avoid aliasing of frequencies above 11 kilohertz, should be from 11 kilohertz on to the maximum. Here is 22.05 kilohertz. Since we don't have an ideal filter, we need to include a transition band here from 9 kHz to 11 kHz to let the filter transition from pass band to stop band with intermediate attenuations. Aliasing is something that is easily perceived by the ear. Hence, we would like to have at least 60 dB attenuation from 11 kHz and up. The pass band can take some ripples in the frequency response, for instance plus or minus 2 dB, corresponding to about plus or minus 25% in voltage. The frequency range from 9 kHz to 11 kHz is the so-called transition band, which gives the filter space to build up its attenuation from 0 to 60 dB to make sure it already has the 60 dB at 11 kHz. In this way, we can formulate requirements for a similarity of our filter, even though we know we cannot reach the optimum. So that's a practical approach. A first and perhaps naive approach is to define the similarity as the quadratic error of the frequency response of our FIR filter to our given ideal frequency response. Mostly this means the magnitude of the frequency response. This has the advantage of being mathematically very simple. This means our goal is to minimize this quadratic error. So assume our desired frequency response is hd of omega, and the real frequency response of our causal FIR filter is h of omega. Then the quadratic error is given by this integral here. So we would like to make this error as small as possible. Observe that we need an integral here because the frequency domain signal is continuous, since the time domain signal is not periodic. Only then would the Fourier transform be discrete over the frequency. But here we have the sinc function with infinite extent over time. Observe that because of this we also cannot apply the discrete Fourier transform because it's made for periodic signals with a finite period. The DFT is usually applied just to this finite period. But the discrete time Fourier transform is for discrete time signals with infinite period. We need to minimize the quadratic error E to find the best approximation with our FIR filter. We cannot solve this problem in the frequency domain, but we can solve the equivalent formulation in the time domain. To obtain this, we use the so-called Parsable Theorem, which states that the power of a signal, the sum of its magnitude squares, is the same in the time and in the frequency domain. This is true for the discrete time Fourier transform as well as for the DFT. So here we have the Parsable Theorem. So the power of a signal is the same in the time and in the frequency domain. The beauty here is now is that we obtain a sum which we can now compute more easily. So we want to obtain h of n. For our ideal low-pass filter, h of t was the sinc function. To obtain a causal filter, we already allow the time shift nt for the ideal impulse response. Using our FIR filter h of n makes causality possible. Plugging this into this equation yields this other equation here. So how should we choose h of n and the delay n of d to obtain the minimum possible quadratic error E for a given length L of h of n?